Hello there, and welcome back. In this video, we're going to continue our journey through special probability mass functions. Up to this point, we've already discussed the Bernoulli, uniform, geometric, binomial, and Poisson probability mass functions, and in this video, we're going to introduce three others: the hypergeometric, the negative binomial, and the multinomial PMFs. So let's get started with talking about what is the hypergeometric distribution and why should we care about it. So let us consider our population P, which we're typically always interested in studying. Most of the time, we do not know the population mean, standard deviation, population size, and the number of possible successes that could occur in this particular population. If we know at least one of them, or possibly even more, usually we can get more accurate representations or probabilities on some particular events. So for example, let us assume there's a few, points in here. So let's assume these represent our values in our population, our objects, the people we're interested in. And let's assume that there are some successes, whatever success means in our context, right? Let's just represent them by stars. So a few things that we're going to notate here. So we're going to be denoting capital N to be the population size. So this is going to be the size of, how many different objects are in this particular population. Now let's assume capital K is going to represent the number of possible successes in my population P, right? So let's assume that population size for this particular example is going to be the number of people that are in my population, and K is going to be the number of people that have anxiety in my population. So what we usually do, since we cannot study the entire population, is we go into this population and we grab a sample from that. So we're going to denote little n to be the sample size. Right, so keep in mind little n is always less than or equal to capital M. So typically this is a simple random sample also. So what are we going to be interested in? So what is the probability that exactly, let's say, 3 people in our simple random sample has anxiety? So this is the type of question that the hypergeometric distribution can answer for us. So let's just define a couple of these parameters, for example, capital N and capital K. So let's assume capital N is going to be equal to 37 people. So for example, that can be the number of people in a cafeteria or a restaurant or something. And let's assume in that particular population there are 18 people who have anxiety. Let's go out and collect a simple random sample of 7 people from that population of size 37. So we're going to let X be the number of people in my sample that has or is classified as a success. And for this particular example, we're defining success as has anxiety. Okay, or who is stressed or whatever. So that means every time we have a random variable x where we're counting the number of successes in our sample, so that should ring a bell with binomial distribution, and capital N and K, so if capital N and K is known, then x is called a hypergeometric random variable, right? So what we want to do is we want to find a probability mass function, P of x, such that we plug in the number of successes that we want, 3, and we get some number back again. So let's just take a look at what that looks like. And we've actually already proved the hypergeometric distribution using our sample space and event space perspective. So let's just take a look at that now. So the probability mass function for a hypergeometric random variable is given by Px of x is equal to ckx multiplied by c n minus k little n minus x all over c capital N little m. So let's just take a look at what each of these elements represents. So c again represents combinations. Remember, k is the number of possible successes in my population, and x is the number of successes in my sample. So this is the combinations of possible successes. and my sample S. So what's this other object? So remember, if K represents the number of possible successes in my population and capital N represents my population size, that means capital N minus K is the number of possible failures in my population. And if I have a sample size of N and I have X successes in my sample, that means little n minus X is the number of failures in my sample. That means this object, Cn minus K, n minus X, is the combinations of possible failures in S, right? So every sample has two structures that comprise it or partition it. That is the successes in my sample and the failures of my sample. So of course they're mutually exclusive. And how many samples are possible, that can be partitioned that way. So there's n possible outcomes or possible values in my population. Little n is the sample, therefore capital N. Choose n is the number or the combinations of all possible samples of size little m, right? So it's pretty much the size of the event space divided by the size of the sample space, and that's pretty much what is going on here, where each of those samples is partitioned into successes and failures, right? So hence we multiply them because we want both to occur. So if you use this probability distribution on our example, so remember capital N was equal to 37, the number of possible anxious people in my population was 18, my sample size was equal to, let's see, what was it? Let's go back. So my sample size was equal to 7, and we want X, and the number of successes in our particular example, to be equal to 3. So therefore each of these values, let's assume, is independent of each other. Then the probability that our hypergeometric random variable is equal to 3 is going to be equal to C18 choose 3. So that's the number of possible successes, and we want exactly 3 successes. Remember, our sample is of size 7. That means 7 minus 3 of those values in my sample is going to be failures. Remember, we have 37 people in our population, so when we take 18 away from them, that's the number of possible failures in my population. And we have 37 people for which we are selecting 7 from them. That is our possible samples. So let's just clean this up a bit. So that's going to be 18 choose 3, and then on the top we're going to have 19 choose 4, and then on the bottom we have 37 choose 7. You can work out these using the factorial representation, but I'm just going to skip you the steps here. That's going to come out to approximately 30.72% chance of that occurring. So that is how you can use the hypergeometric distribution. And of course you can consider problems, what is the probability that I have more than 3, or less than 3, or at most 3, or exactly no people are anxious in my sample. You could answer all those similar to as we have before. Since X is a random variable, it has an expected value and a variance formula, so let's just write them down here. So the expected value of a hypergeometric distribution is going to be n times capital K divided by capital M. Now notice here that capital K is the number of possible successes in my population, and capital N is the number of possible values in my population. So capital K over N is the proportion that is associated to the number of anxious people in my population. So if you remember from the binomial distribution, this is similar to the formula n times p, which is the expected value for a binomial random variable, right? So there definitely is some similarities here. And what about the variance formula? So the variance formula for a hypergeometric random variable is going to be equal to n times k over capital N times capital M minus k over capital N times capital M minus n over capital N minus 1. So again, what is each of these things? So this is pretty much the probability of success. If you look at this next term in a little bit of different way, that's the same as 1 minus capital K over N if you divide capital N into each of those terms. So if K over N is the probability of success, that means 1 minus K over N is the probability of failure. So this formula, variance of X, is similar to that of NP 1 minus P from the binomial distribution. And of course one may ask, well, what is this thing at the end, this n minus 1? So remember, since we now know a parameter, actually two parameters, k and capital N, then we need to account for the fact that if we get all of the values in my population, I should have no variation or no randomness or no error in my particular sample. So notice that this numerator for this last part, if we have the entire population size, that means little n is equivalent to capital M. The variance is going to be 0 because we're going to have everybody in my population in my particular sample. Some people will refer to this as the square of the FPC, or the finite population correction factor. But we're going to be looking at the FPC at a little bit later time, and it's not really an important thing, at least to discuss for now. But if you hear the finite population correction factor squared, or FPC, that's just capital N minus little n over capital N minus 1, and it does have purposes when you have parameter information that you didn't have before, and it pretty much allows us to correct for that difference. So let's just ask one more question, just as a little example for this expected value. So example, what is the expected number of people in a sample of, let's say 20, let's go 22, and a sample of 22 who will be anxious? Okay, so if we know the population size and the number of anxious people in my population, then we can use the hypergeometric distribution to approximate that. So that's going to be our sample size times the number of possible successes or stressed people in my population divided by the population size. So we have a sample of 22, and there's 18 people in my population, and there's 37 people total in my population. So that's going to come out to approximately 10.70. So that means if we grab a sample of 22 people, we would expect anywhere between 10 and 11 people to be anxious in that particular sample. So if you get a sample and we have exactly 0 anxious people, or all of them are anxious, so all 22 of them, we would expect that possibly that our sample is actually not simple and random, but actually, maybe there's some other underlying issues going on there that we may need to investigate. So now that we have some basic idea of the hypergeometric distribution, now let us take a look at the next distribution. So the next distribution that we're going to be taking a look at is called the negative binomial distribution, and it models the random variable x, where x is the number of independent Bernoulli trials until you obtain r successes. So we've actually already looked at a special case of the negative binomial distribution. So let's take a look at what this distribution looks like when r is equal to 1. So it's going to be the number of independent Bernoulli trials until you get your first success, right? So that means we're looking at the sequence failure, 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 all the way out to failure, 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 capped off with a success. So what distribution models this particular structure? So if you remember, this is actually a geometric random variable if you only want one success, right? So the negative binomial distribution actually is an extension of the geometric distribution. But instead of capping off at one success, we sort of continue this iteration until we get, for example, 2 successes or 4 successes or 10 successes or something like that. So let's take a look at a special case of r is equal to 2, right? So now we're looking at sequences such as failure, 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 success, failure, 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 and then finally success, right? So we want 2 successes, therefore we're going to stop on this particular one, right? So how many x's is that? So that's 1, 2, 3, 4, 5, 6, 7, and 8. So this is pretty much x is equal to 8. So what is the probability that I get my second success on my 8th attempt? And my one success is somewhere else in this particular sequence, and all of the rest of them are failures. So even though this is an extension of the geometric distribution, it sort of has like a binomial distribution flavor associated to it, right? So notice, since we have a success here, we do not want that success anywhere else. Therefore, we will be permuting the other 8 minus 1, or 7 rearrangements of that, right? So how many rearrangements of 3f's, 3f's, and 1s are there? Well, we should know that there's going to be C71 of them, right? And keep in mind this last success occurs on 8, but it will not be permuted amongst the rest of them. What about r is equal to 4? Let's look at an example of what we're looking at here. So if we have r is equal to 4, then one of the possible scenarios that we're looking at could be failure, success, failure, 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 success, right? We want 4 successes, so we're going to keep on going. Failure, success, and then 1, 2, 3, 4, 5 failures, and then finally a success. Notice that we only want 4 successes, so we're going to stop here. And what x is this? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Right? So how many rearrangements of the other objects are allowed for this particular structure? Because there's definitely several of them. So that means we have 13 objects that are going to be rearranging, and we have 3 successes that we want to permute. If we're focused on the successes, then that's going to be 13, choose 3. Or you could focus on the number of failures, and you would of course get the same exact number of combinations. So using this structure, notice that this is equivalent to C 14 minus 1 over 3. And what is 3? Well, 3 is going to be 14 minus 1 over 4 minus 1. Because technically we are stopping at 4 successes, so that's going to be the number of successes we want, which is going to be r. And 14 is the x value for which we need in order to get that certain amount of trials until we get r successes. So using this pattern, we can easily extend this to the general negative binomial distribution. And that is going to be equal to Pxx is going to be equal to C x minus 1 r minus 1 times 1 minus p to the x minus r times p to the power of r. So again, what is this? So 1 minus p is going to be the probability of failure, p is going to be the probability of success, r is going to be the parameter that represents the number of successes we want to get until we stop our sequence. And if we have r successes and x trials, that means x minus r of them is going to be associated to failures. And Cx minus 1, r minus 1 is the rearrangements of all the values preceding the last success. That means x minus 1 values there, where r minus 1 of them are going to be successes, right? Because the last r is hanging out on the very end. So this is the negative binomial distribution, and of course it has an expected value formula. The expected value, or the expected number of trials until you get r successes, where r is the number of successes you want and p is the probability of success, is going to be equal to r over p. And if you remember the expected value formula for geometric, that was just 1 over p, right? So now we want r of them, so we pretty much have r over p, so very close connections there. And I leave it to you to sort of think about, the variance formula for a negative binomial. So maybe you recognize 1 minus p over p squared and which one this is. And if we multiply this by r, that gives us the variance formula for a negative binomial distribution. So now that we have just a basic idea of what the negative binomial distribution represents, now let us take a look at an example in real life where we may want to use this particular distribution to solve it. So let us consider this particular scenario. Suppose that a game that you are playing has a probability of winning of approximately 32% chance. Suppose you give yourself a reward if you win 3 games. What is the probability that it takes you exactly 10 attempts to win all 3 games in order to get your reward? So let's just map out a particular scenario for which is described by this problem. So let us look at the sequence of events. So we want exactly 10 trials until you get 3 successes. So that means the last attempt must be a success. So that means one of the scenarios, let's assume we get a success, our first 2 successes there, but then that means the rest of them, so 3, 4, 5, 6, 7, 8, 9, must be all failures in order to get our 3rd success, for where we want to stop on our 10th attempt. Now keep in mind these 2 successes could literally be anywhere in this permutation, therefore we need to rearrange them in order to account for all of the possible scenarios where we get our 3rd trial on x is equal to 10. So this is indeed a negative binomial distribution problem. So we know that x is going to be equal to 10, the number of successes that we want is going to be equal to 3, and the probability of success for winning any of these games is 32. So we of course need to make sure that the probability of winning is independent regardless of how many attempts we have had, else it becomes definitely more complicated. So we need to assume, at least for this problem, that each of these games are independent of one another in terms of the probability of winning. Not all games are like that. Of course, there's some personality things you need to take into consideration when you're playing a game of chance, but let's just assume they're independent just for the sake of this problem. So if we know these things and we're assuming independence, that means x is a negative binomial distribution or a negative binomial random variable. So that means the probability that x is equal to 10 is going to be equal to c 10 minus 1, 3 minus 1. So what is this 10 minus 1? The 10 minus 1 is going to be the number of trials that can be rearranged. 3 minus 1 is the number of successes in that particular rearrangement. And then we're going to have the probability of failure, which is going to be equal to 1 minus 0.32 to the number of failures. So we're going to have 10 minus 3, right? So 10 minus 3 is going to be these 7, 1, 2, 3, 4, 5, 6, 7. That could be literally anywhere. And then p to the power of 3. That's the number of successes, 1, 2, 3, that we definitely want. So that's going to be C9 choose 2 times 0.68 to the power of 7 times 0.32 to the power of 3. And then once you work that out, you should get an approximately 7.93% chance of that occurring. So that is the negative binomial distribution. So now let us take a look at the last distribution, which is called the multinomial distribution, which is an extension of another problem. So let's look at the multinomial distribution. So the multinomial distribution, so just by the name, maybe this is an extension of the binomial distribution, and it indeed is, right? So let's just look at the binomial distribution and see how we might, or maybe we want to extend this, right? So let's assume we want to solve the probability of getting, for example, 2 heads when flipping a coin, and let's assume it's not a fair coin. So let's assume that the probability of getting a heads is 0.49. And let's assume we flip it where we flip it 5 times, right? So we can solve this via a binomial distribution problem. So that means we're interested in heads, heads, tails, tails, and tails. And of course, these all can be rearranged. For example, we can have 3 tails, 2 heads, or TH, TH, T, or any rearrangement thereof. So this is definitely a binomial distribution problem. So what is the probability of this particular event? So that's going to be the probability of h to the power of 2 and the probability of t to the power of 3. But how many rearrangements of them are there? Well, if we were to treat all of these objects as different, so 1, 2, 3, 4, and 5, there's definitely going to be equal to 5 factorial rearrangements of all of those different objects. But if we treat these h's as the same, that means there's going to be 2 factorial of those h's that we cannot see the difference between, and there's going to be these 3 t's that we cannot see the difference between. So by fundamental counting principle, there's going to be this many of these rearrangements that are going to have this probability, right? And as we already know, this object is the combination formula. That's precisely C5 choose 2 if we're focusing on the number of heads. So there's 2 heads. And the probability of heads is 1 minus 0.49 to the power of 2 times the probability of tails, which is going to be the complement, which is going to be equal to 0.51, right? So that should be 0.49, not 1 minus 0.49, right? So that is going to be your probability, once we have everything written out, which is going to come out to 31.85% chance of occurring. So that's the binomial distribution. So how can we easily extend this problem? So keep in mind, the question that now we want to answer is, what if we have more than 2 possible outcomes? So which description of the binomial are we now trying to break? Now we're trying to break the Bernoulli trial assumption, right? So now we don't want a Bernoulli trial. We don't want, a success or a failure or a heads or a tails or a true or a false. Now we want a bunch of objects like red, orange, or blue or something. So let's look at a basic pedagogical example to sort of illustrate this. Right, so let's assume we have a bag of marbles, and there's so many applications that can be modeled with this. So let's assume our bag of marbles contains 5 red marbles. Let's assume it has 7 orange marbles. If we had just 0 orange, it doesn't really make any sense to talk about them. And let's assume we have 8 yellow. All right, so that is my sample space. So the number of objects in this bag is going to be 5 plus 7 plus 10 plus 8, which is going to be equal to what? So that's going to be equal to 12. 12 plus 8 is going to be 20, plus 10 is going to be 20. Right, so we have 20 possible objects in that bag. So now what are we going to do? Now we're going to grab a simple random sample of 10 marbles from this bag. Right? So let's ask the question, what is the probability that our selection has this particular structure? So let's assume we have 3 red marbles selected, not 0 again. Let's go with 2 orange marbles, 4 blue marbles. Now keep in mind, I don't technically need to tell you how many letters there are here, because we're grabbing 10 of them, right? 3 of them are red, 2 of them are orange, 4 of them are blue. Therefore, how many of the rest are going to be yellow? That means we have 3 plus 2 is 5 plus 4 is 9 marbles already described. That forces the last one to be exactly 1 yellow. So technically, we don't need to tell you explicitly, what that number is, right? So what is the probability that we have 3 red, 2 orange, 4 blue, and 1 yellow marbles in our selection? So this is definitely a multivariable distribution, which is actually very cool. Therefore, we're interested in events such as, the probability of red, 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 orange, orange, blue, 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 and finally yellow, right? Now keep in mind there are several rearrangements of these, right? So let's just find the probability of this particular event, right? So the probability of this particular event is going to be equal to, so what do we have? So there's going to be 3 reds out of a total of 30, so that's the probability of selecting 1 red. We want exactly 3 of them in our, actually no, there's 5 red marbles, right? Right, so let's go back up. There's 5 red marbles in there out of a total of 20, right? So that gives us 5 divided by 20, no, 30. It's 30, right? Yeah, I don't know why I wrote 20. It should be 30. Yeah, there we go. I was like, yeah, I said 30, but I wrote 20. I don't know why. So 5 out of 30 probabilities for the probability of red. So this is the probability of red and red and red. Now we want 2 orange. So how many orange marbles do I have in my bag? So there's 7 orange total. Right, so the probability of selecting orange is going to be 7 out of 30. So the probability, how many do we want? We want 2. So that's going to be to the power of 2. Now how many blue marbles do I have? So the probability of selecting 1 blue marble is going to be 10. And keep in mind we're selecting them at the same exact time, so each of them is going to be 10 out of 30. So it's going to be 10 out of 30 to the power of 4. And then we want 1 yellow, and there originally was 8 of them, right? So that's to the power of 1. Now this is just the probability of one rearrangement. There are several rearrangements that you could get here. So if we were to treat all of these objects as different, that would be 10 factorial, but there are 3 reds that are in repetition, there's 2 oranges that are in repetition, there's 4 blues that are in repetition, and there's 1 yellow that is in repetition, right? So this is the probability of the event of interest. And once we work all that out, you should get something, if I did it correctly, as 0.0105 as your final answer. Right? So that is at least an example of the multinomial distribution. And let's just write out the exact form of it, so the theoretical one. So again, this has several random variables. X1 is going to be the number of red marbles, for example. X2 is going to be equal to the number of orange marbles. And technically you could have k different objects in here. So we're going to let k be the number of different objects in my sample space that I'm selecting from. And this is going to be equal to what? So this is going to be equal to n factorial. So n is my size of sample being drawn, which could definitely include repetition, so we need to take that into account. So we want exactly x1 of them for object 1. We want x2 of those, and all the way out to xk of those, right? And keep in mind 0 factorial is equal to 1, right? And then we have the probability of x1 to the power of x1, and then the probability of 2 to the power of x2, all the way up to the probability of xk, where each of these are associated to your original population that you are selecting, right? So what is the expected value of each of these random variables, x1, x2, xk? So you should notice that each of them is very similar to a binomial random variable. So we can sort of look at them in isolation. So the expected value of xk is the sample size times the proportion of my population that is associated to that particular random variable, and the variance of that particular random variable is going to be n times the probability of success for that random variable times 1 minus the probability of success, or the probability of failure for that random variable. So this is the multinomial distribution and all of its wonder. It's the very first multivariable distribution that maybe you've been exposed to, and it's not actually that hard when you take a look at it. Of course, when you drop independence and you start looking at marbles before you look at the rest, definitely the problem gets extremely difficult, but we'll maybe consider that at a later time. But for now, those are some of the most common probability mass function distributions that are defined on discrete random variables. So in the upcoming videos, now we're going to take a look at how we can model the probability of continuous random variables. So I hope to see you there. Take care.